Okay, so it's gas exchange and fish and insects, and I've done a bit of prep just to speed things up a bit. Remember, we are still applying Fick's law. Rate of diffusion is proportional to the surface area multiplied by the concentration difference divided by the thickness of the barrier or the distance, the diffusion distance. Just a quick aid memoir here. I've drawn a gill. So this is the main structure of the gill. And I'll just label that gill. So that's the gill. Then these that stick off are gill filaments. Gill filament, and then on the gill filaments we have lamellae. I'm going to draw the lamellae on now, so they stick up like that on both sides. I'm not going to draw any more. So yeah, so these are lamellae. So we can say that in terms of surface area, it's got many lamellae because each gill has got many gill filaments, and each gill filament has got many lamellae. Okay, we're going to zoom into one lamella. This one here at the end, this is now face on. This diagram over here, this is a face on picture. So I'm looking at it this way. So it's like a, how can I explain it? It's like a Pringle. If I want a Pringle face on, I see it as a disc. If I put it side on, I see it just as like a line. And I know they're slightly curved, but bear with me. So that's my side on Pringle. Now it's face on. So I've got at the bottom here, this is a bit of the filament. And it's really this diagram that you need to know. So there's our filament. And this is the lamella. And in the lamella, again, it's really thin, but it's got a really rich blood supply. So there is blood coming in and out. So it kind of comes in and out. So there's an artery and a vein here. Let's say artery here and vein there. So the blood's flowing. Let's put like the capillary network on as well. So there's like a load of blood vessels in here. It's highly vascularized, which means it's got a rich capillary network. Yeah, so blood is flowing in effect that way. Okay, so that's my surface area pretty much sorted. I can talk about the gill, and I can also talk about each of the lamellae has a large capillary network, like you would say for the lungs as well, for the capillary network around the alveoli. And direction is important on this. So your blood's flowing from artery to vein. It's therefore flowing from left to right on the diagram. Therefore, you need to know that water flows in the opposite direction. So water is going the opposite way. And if we graph this, because this is how we get our like concentration difference. So let's graph it. Let me just shimmy this up ever so slightly. So this is the distance, and we're going to say this is the distance along capillary from the arterial end to the venous end. Okay, and in terms of the concentration of oxygen, well, it's coming to the gas exchange surface, so it's going to have a low concentration of oxygen. So in the artery that it comes in, remember, it's much like the pulmonary artery in our lungs. Well, that feeds our lungs. It comes from the heart. It's the only artery that carries deoxygenated blood. This is deoxygenated blood. I'm not putting zero, but I know what I mean. And then as it goes along the capillary to the vein end, it's going to increase, and it's flowing that way. Yeah, so it's going to end up at, let's say, like fully saturated. So this is like 100% at the top. And then it's like, well, I need to put water on here as well. So they often show water on this graph as well. Well, water's coming the opposite way. So I start over here, as in when the blood enters, it's like I'm taking this capillary here. I don't know if you see my red splodge. I'm graphing this capillary here. I'm now going to say water's coming in at this side. Well, the water is going to be fresh water. Let's say it's going to be fully saturated with oxygen. So here's the water coming in, and as it comes through, it's flowing that way. So that's our water. It's always above it. So I was wrong to say that the blood is leaving with 100%. It can't, because if the water comes in with 100% oxygen, so oxygen is going to diffuse into the blood. So again, just to make these numbers easier, let's again just show this out as like a straight line rather than being a graph. So that's what it kind of looks like when it's a graph. So this is going to be the same thing. This is our blood. This is our water. Water's moving that way. Blood's moving this way. So this is where there's fresh, there's 100% oxygen in the water here and in the blood. And sorry, I'll start over here. There's almost like zero oxygen in the blood that's coming into this system. So if I get some diffusion happening, I might get this is going to go to like 90. This is then dropped to 90 because it's water flowing. 10 of the water has gone out, so this is 80. As in, I've got a diffusion gradient all the way along. This is now 80, and it's going to 60. This is now 40, and it's meeting water at 20, and this is now 10, and it's meeting blood with only 5 in it. Yeah, so I've always got an increasing oxygen concentration in the blood, and I've always got a decreasing oxygen concentration in the water. And it's just knowing that this is a counter current flow mechanism. Counter current flow, ENT, not ANT. It's not a fruit, dried fruit. Counter current flow mechanism. So it maintains a concentration gradient, maintains conc gradient over entire length. I can't spell length. I can spell current, but I can't spell length. Length of the capillary. Let's try to be an I. So that explains our concentration difference. So surface area, just describe everything. Many. Concentration, you need to talk about the counter current flow mechanism. Because water flows in an opposite direction to the blood, the blood's always encountering water with a higher oxygen concentration, and therefore there's always a diffusion gradient of oxygen into the blood. This counter current flow mechanism also works for heat as well. So lots of animals have this as like heat exchanges in their nostrils, or birds have it in their legs. Last thing is just distance. And it's just like if you watch the lungs video, just being really clear about epithelia and like distance. So if you think, water is moving over a capillary, it's not having to move through a cell into the capillary like it is in the lungs, like through the alveolar epithelia, through the capillary epithelia into the blood. It's just one thing here. Yeah. So I've literally got, just to kind of show the lamellae. So let's take this one here and let's make it a bit thicker. So there's our lamella attached to the filament. And then on here is going to be its capillary sticking off. I know this is highly enlarged now, but there's a capillary, and there'll be a capillary on both sides. So this is the epithelial cells of the capillary. So those are all cells. And then there's going to be blood cells kind of like squeezing through. It's harder for fish because they have nucleated red blood cells, so they're not as small as ours. So yeah, so their blood is going through, so it's going into the page or towards your eye, and and oxygen is diffusing, and water will diffuse if osmosis is, if the blood of the fishes has got a more negative water potential. But yeah, oxygen only has to diffuse through one cell of the capillary to actually get into the blood, and that one cell is a flattened cell anyway. I can see why fish get a lot of parasites in their gills, because the parasites have got easy access to sucking on the blood. So just in summary, get my pointer going. Rate of diffusion, it's high because of the surface area. They have many gills. I didn't say that at the start, but you don't have one gill. You normally have like 8 or so, on both sides of the mouth. and they have many gill filaments and many gill lamellae, and each lamella has got many, a dense capillary network. So I can say a good description of their concentration. There's nothing about ventilation, so you don't have to say that the fish like causes water to move into its mouth over its gills and out again. So on Oesophilus, it's just focusing on the countercurrent flow mechanism, and the distance is really small because there's only one cell to go through. Okay, and it's important because there's far less oxygen in water than there is in air, and it's dense to move as well. So it's a hard job living in water and getting enough oxygen, especially if you're a very active fish. So that's fish gills. So let's do insects quickly. Again, I've sketched this out. This is just the air outside. This is inside insect. So in its abdomen. This is a spiracle. A bit like guard cells. They're just kind of like one, this is one thing kind of cut through. And it can pinch, it can close and open. This is its tracheae. And it branches. Smaller and smaller ones. And therefore that's our surface area bit. Yeah, they have a branching tracheal system. So surface area, tick. Next, let's go for concentration difference. So how do they keep a high concentration? Well, it isn't just passive diffusion into here, because we move our ribs and move our diaphragm to cause ventilation. So an insect can do abdominal pumping. So it can pump abdomen. Remember, insects have a head, a thorax, and then an abdomen, and then they have like 6 legs that come off. Sorry for the diagram. And they can pump their abdomen up and down, and that helps to kind of squeeze the tracheae and therefore move air into and out of the tracheal system. So pumping abdomen gives you a bit of concentration difference. The interesting bit really is the diffusion distance. So over here I've got a picture of the end of a tracheae, and these are the body cells that it's feeding. The cells are surrounded with tissue fluid. Okay, so I tried to get it in, but there's a few white gaps, but trust me, this is tissue fluid, just like we have tissue fluid. And that tissue fluid is going to end up getting into this tube. So this is also tissue fluid as well. And that's important because gases, so there's going to be oxygen, and nitrogen, but it wants the oxygen. It wants to get the oxygen from the air. This is air in the tracheal system. It has to dissolve before it can get into a cell. Okay, and therefore they keep the amount of water, the volume of water at the end of the tracheae is kept to an absolute minimum. So there's going to be lots of air for fast diffusion, and then so fast diffusion, then it has to dissolve, much like it has to do in the alveoli. It has to dissolve in the fluid that lines our alveoli before it can get through the cell. So it has to dissolve and then diffuse into the cell. And if the tissue fluid came to here instead, it'd have a far further distance to have to diffuse through the water. Diffusion through liquids is far slower to gases, as you know. So yeah, so it keeps its diffusion distance is really there's only, and I'll write it out. Yeah, so in terms of distance, yeah, there's only a small volume of fluid, I could say tissue fluid, in the ends of the tracheae. Therefore, yeah, most diffusion is in air. Therefore, faster. Yeah, diffusion is far faster in air than in a liquid. And then they like to ask about this in terms of these kind my graphs. So I've got time here, O and C, O and C are when spiracles are open for O, C for closed, oxygen concentration in the tissue, and it's absolute common sense that when the spiracles are open, the oxygen concentration around the tissue is going to increase because air can get in, and oxygen diffuses because the cells are using the oxygen, so it's going to make the tissues aerobic. And then they close their spiracles and the oxygen decreases. Yeah, so you end up with this coming down line because fresh air can't get in. It's like us holding our breath. The air in the alveoli would just start to kind of have less and less oxygen and more carbon dioxide. Then it opens again, and then it closes again. So insects are opening and closing to try and maintain the oxygen concentration, and they do this because insects are tiny generally, and whenever they have their spiracles open, they're going to be losing water. Okay, so water is going to be evaporating from the tissue fluid into here. It's going to be diffusing out. So the air in this tracheal system is going to be 100% humid. Oops, pen. So all this is going to be 100% humidity. And therefore, if outside is a typical day of like 60% humidity, relative humidity, there's a diffusion gradient out all the time, and therefore it closes its spiracles to prevent that water loss. So if you had the spiracles open all the time, the tissues would get far more oxygen and they could do more things. However, like leaves, they are really limited. And therefore, if they're struggling to have a source of water, they have to open and close their stomata to get to the best compromise between getting the oxygen they need for aerobic respiration and not losing too much water. So you can really apply, it's very similar to photosynthesis and leaves in terms of carbon dioxide and water loss. So yeah, these spiracles are very, use your guard cell knowledge. And that's why bees buzz, because they are forcing air into and out of open and closed spiracles, and therefore you get this buzz sound. I always think if your fingers were small enough, you could play an insect. If you could cover the holes up, it'd be like buzz. But that's a dream. Anyway, that's 18 minutes practically, so that's a good time to finish. Hopefully you found something useful. Remember, I do take requests. I've been requested to do one on proteins, which I will do next week.